hopefully that picks me up good enough. Basically what we're doing is working our way through different ways to solve limits. All right, so as long as you know what a limit is, and then you can memorize this list and know how to work that list of how to calculate limits, we're going to be in good shape. Okay. Some of the finer points, maybe it'll take you a week or two, but we'll get it. Okay. So you learned, let's see, yesterday we talked graphical limits, so right? So if I gave you a graph, we could say that the limit as what? X approaches?
As x approaches to
of?
F of x equals 1.
There you go. Okay. Graphically, because we can see that point, right?
Numeric, I believe that.
Numeric limits come when we have a function. Okay. So if you are, here we're not given the actual function like y equals 2x, right? So numeric limits are applied most of the time when we have something like this. And you probably have this one just about memorized, right? So this is graphical. There are a couple ways to do numeric limits. Okay, the first one is just, let's say you're asked the limit as x approaches 2 of x squared. Any guesses? Why do you say 4?
2 squared is 4.
Yeah, that's it. Okay. Number one numeric limit method is just the plug and chug. Okay, so we can do that, right? There you go. Because at the x value of 2, the y value is 4, right? That's that point on the graph. You just plug it in. 2 squared is 4. Okay. So if that's an option, always try that first. Okay, this is your first limit solution method. Okay? Always try that first if you have a function.
So with the numeric, it's just lim of x squared, it's not lim of f of x squared?
Here's another way to write this. I could write this that way too, right?
Yeah.
Okay, then I could write this like that as well.
Cool.
Right, so either of these works in that spot. Makes sense?
Yeah.
Okay. So, yeah, if you see that, just know you're still plugging into the function. You're just evaluating the function, okay? I think you can handle that. Okay, it does get messier. Okay, what happens if we have a function that has a hole in it or something? Okay, we can't plug and chug because there's nothing there, right? So numeric limits, which, and you've actually seen this before. Let's check out
Whoa. I got a
Okay, this has a hole in it. So if I plug and chug, right, just plug 9 in, right? Okay. That's not an answer. Okay. This is what we call an indeterminate form.
So it's just indeterminate.
Okay. And what that means is that it doesn't help us solve the limit. Okay. So we have to find, basically what it means is find a different solution method. Okay? That's what that tells us. There are several different solution methods that we can use at this point. Graphical would work on this problem. If you graphed it, it would show a hole, and you could still determine that spot. Okay? So if you graph this, you can still use that method. Numerically, plugging it in didn't work, but we can use what you've seen before. This will
Super close numbers to 9.
Yep. We want to get really close to 9 from both sides. So this table's probably going to look familiar from continuity last year. What's a number really close to the bottom of 9?
8.999.
Right? And?
8.99.
And?
8.9.
Okay, and then?
You have to do the whole chart. You can't just do 9.001.
You need to do all of them.
Wouldn't that be backwards?
Because here's why you need to do all of them. These two numbers might give you a good answer, but there are functions that bounce really fast up and down. This one might give you a funny number, like way far away. So if you got to do at least 3 to see if it's bouncing up and down. Okay. I can show you one, sin x over x, but we need to make sure that these are consistently approaching that same number from both sides. Okay. So plug them in to, right? And then remember the easy way to do this. We would want 9.001 minus 9 divided by root 9.001 minus 3, right?
Right, the 3 would.
Wouldn't didn't that just do the back up there? Didn't that do the root of 9?
Oh, it did. I didn't move it out, did I? So second entry.
Yeah.
Yep, I made that. There we go. Minus 3. Thanks for that. I just. Okay, so
there we go.
6.001, right? Then you can do second entry. Go in there, delete a 0. Right? There's your next answer. So use that to your advantage.
So would it just go down by the
So yeah, this one goes 6, 3 zeros, 2 zeros, 1 0. So what are we approaching? 6, right? And I did.
So it's one that would be 6.
This would be 6.01. So this side's approaching 6, right? We need to verify it with this side as well. Okay, so. Whoa, that's not what I typed. Must have been what I typed. That's not what I wanted to type. Right, so there's 5.001. 998. So what you would find out if you did all those calculations,
Or that 9's limit would be 6.
those are the numbers you get. So this is going to 6, right? And this is going towards 6. That's your answer. Okay, so you would write the limit as x approaches 9. The function equals 6. Okay. The numeric limit solution. We use it very rarely.
So is that the second choice or one of the last?
It's one of the last, honestly, yeah. Your number 1 is plug and chug. Okay, then
Number 2 is graph.
So if you would've
most of the
got-
time, we're gonna move into an indeterminate form past that point, and you can use algebra or what's called L'Hopital's rule. Okay, so this will be very low on your list.
So if you plug it in, and as long as you don't get 0 over 0, whatever, then you're good.
Yep. If you don't get or 0 in the denominator, that would probably mean does not exist, but you'd want to check it. But 0 in the numerator is okay. That's 0. You can also do this on the table feature of your calculator. Do you want me to show you that?
Yeah.
Um,
You can do it on the table.
Put the function in y equals. Plot off. It was x minus 9.
Minus 3.
Okay. Let's go to table set. You'll want your table start value to be 9 because that's our x. And if you put 0.001 as the change, we're going to get this number and this number. Right, so error at 9, because there's a hole, but 9.001 and 8.999.
How do you do that to start using the table in the table set?
Put it in y equals,
Okay.
table set, start value of 9, and then your change. Now the next one I would do is 0.01, and it will give me 9.01 and 8.99. This is a little less tedious than the last one. Right. Good? So, a couple different ways to manage those, yeah? Your book does not put the tables in this format. And it drives me crazy because it's not as neat. It doesn't show you the left and right aspect of it. The table in your book would look like,
Oh, I see it, that's weird.
they do it vertically. So
Yeah.
they would put like x approaches 9 from the left. They would put their values, okay, and they would evaluate with their numbers. Then they would put x approaches 9 from the right. Then they would evaluate. Right, so
Tonight will we, but tonight will we have any indifferent form from plugging and chugging?
this would be 6.01.
So it's a more complicated version of what you just did.
I think it's messier.
Yeah.
I mean, what do you see from the left? This value approaches 6, and this value from the right approaches. But look, see how much more work is there? It's just, it's not as neat and clean. It does not show you the left and right. I prefer the left one myself, but your book is all in this format, so be careful.
Why
there.
did that?
Yeah, I don't know.
Offers,
This book,
call.
Yeah, pretty much. John Rogowski, the book is actually a very formal calculus book. Like definitions, theorems, proofs, lots of theoretical math in it instead of more of a conceptual approach, which is the way I'm approaching it with you. Either way works, but okay. Let me show you one that doesn't work real quick as numeric limit. Do you see it? This should be x. Yeah, pi over x.
So it's not a pi over x?
Yeah. So if you plug 0 in there, it gives you that fraction, right? It's undefined, so we can't plug and chug as always. So that first solution method is out the window. If you graph this, let me just go and graph it. Sine. Always make sure your calculator's in radian mode. We are in the real numbers now. Okay. Let's go to zoom trig. If you're working with trig functions, you can do zoom trig, and it'll get you a good window for those.
What the heck?
Pretty.
Exactly, right? So it's kind of being like a normal sine function, then it is a... Now I'm happy, right? Zoom in.
Like every teenager in the world.
Okay, can you do that graphically?
No.
Okay, try again.
No?
No, it's just gonna keep on going.
Funny every
Did you see how it bounces up and down? I was telling you, if it bounces up and down, it's just funky, right? So,
Zoom again.
why?
Yeah. One more time.
Just to see.
Yeah.
I've had students in the past that would sit here the rest of the hour and go zoom to enter, zoom to enter, zoom to enter, zoom to enter. It's never gonna change. You're wasting your time. I know, but it's fun, Mr. Arthur.
What have I done?
Sorry, you gotta do it again.
No.
One more time. You just say. Keep going until I can't see it anymore.
We evaluate, so around 0,
Will that eventually become solid?
that graph,
Yeah.
you mean like stop doing this?
Like if you zoom in enough, will it get to the point where you can see?
If you zoom in enough?
Yeah.
No. It's, anywhere you zoom, it just does this. And numerically, if you look in your book, basically what it does for these numbers, it alternates positive, negative, positive, negative.
What? Even if you do like 0.001.
Yeah.
Jeez.
And then this side, I think it would probably be negative, positive, negative, positive. So the numbers you pick obviously do not, they're not consistent.
So we're not able to find the limit?
No, the limit does not exist.
That's cool.
Okay.
The cake is alive.
Watch out for sign.
Okay, so we would say that this does not exist. Okay. What does an infinite limit look like?
When
When
they-
it's
we should put an infinite sign on the side of it, so it never touches. Right? When it's approaching but never, that's what we had yesterday with 16, or figure
Yeah.
3, the number 6.
Oh, yeah.
Okay, how about this one? This should be, I want to be quick because we're running out of time. Do you remember what the graph of that looks like?
It's just one line that goes like this.
It's a rational function.
Yeah, so you have two different lines.
Looks like this.
Oh, just kidding. Yeah, I thought it was the ray two thing.
Okay. So the limit as x approaches 0 from the left. This has no two-sided limit, first of all, right? But we can do left and right limits. If you do it numerically, all we're doing is the left side. Right, so these numbers are going to get really big really fast. Okay. Did I draw that wrong?
No.
Yeah, I did.
Yeah, I can.
It should be reflected. These should be negatives.
Oh, but you already drew that.
Oops.
You
Sorry.
messed up, Arthur.
Can I just
I-
like put
you
a
know what?
negative in front of the 1x?
It happens.
Is that what you're saying?
You could put a negative in front and that graph would be correct.
Yeah, okay.
Okay, but you can see as you're going to get really big negative numbers here. So this would be like negative 1,000, negative 100, and negative 10. See how they accelerate really fast? I wrote everything backwards.
Why?
That's my problem. Sorry.
I have erasable.
Got
pencils
dyslexia there for a minute.
Pretty sure that's just called pencil.
here. No, it's an erasable pen.
So, pencil.
So negative
It's
10.
not a pencil. It doesn't use. Yeah.
So your answer would be negative infinity there, graphically and numerically, okay?
So is that only for those types of graphs, or can it happen in other cases?
Yeah, it can happen. It'll show up. If you use your analysis techniques, it'll show up. Right.
So it goes by the place it's in, like the place value. That's cool. I don't know why I'm so intrigued by this, I am.
Because it's math,
You mean,
it's neat.
this is the thousandths place, so it's 1,000?
Yeah.
Yeah. Okay, there you go.
Huh? Oh, it's not a good idea.
It is, yeah. Even if it's like to your back, it's all amazing.
You could- You're with